Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. All right, this is our module number 4, part 2, Deep Neural Networks. In part 1, we covered some basics, right? We talked about what is this idea of neuron. What do we call neuron? What is forward propagation versus backward propagation? We talked about different activation functions and different solvers. In part 2, we will be talking about one of the most important topics when it comes to training a neural network. We will talk about the concept of overfitting and how we can fix it. There are different ways of fixing overfitting, namely, regularization techniques, basically. We will talk about L1, L2 regularization. We will cover dropout and early stopping and data augmentation. And then finally, in this part, I will talk about the concept of tensor and how we are going to store different type of data sets in a tensor. Okay, without further ado, let's get into that. Okay, so how to handle overfitting in neural networks in general. If you watch the machine learning review section of the course, you're familiar with the concept of overfitting, right? So in order to give you a quick recap, imagine this is the data, the red dots are the real data, and we want to come up with a model that can capture that pattern in the data. So the model on the left, let me call it number 1. This is obviously an example of underfitting. The model is too simple. This is a simple linear function model, and then it's too simple. And that too simple model is not capturing necessarily the nonlinearity in the data, right? The model does not have the capacity to learn the data. So this is not necessarily a good one, right? Actually, it's not a good model. On the far right hand, let's call it model number 3. This is a model which is unnecessarily super complex, right? It is capturing all the nuances, all the noises in the data. Maybe it's memorizing the train set. This is also not necessarily a good model, but I would claim that I would rather to have model number 3 compared to model number 1. So I would say I would prefer model number 3 to model number 1. So this is a sign of preference, right? The reason is that a good model is a model that can at least overfit in the train set, right? So it means that the model is complex enough that can literally overfit the train set. And then if I have that model, I can go ahead and prune it back to regularize it back to a less complex model, right? I can go from model number 3 to an optimal model, let's say model number 2. This is an ideal fit, right? But it is hard for me to go from model number 1 to model number 2 because going from 1 to 2, it means that I'm missing something, right? So the model is not capturing the pattern. I have to change the structure. In neural network, I need to think about adding different layers, changing activation functions. So I have to make the model more complex. But if I have some model like this, number 3, the path is smoother because now you know that you have a model that can overfit. Let's go ahead and use some regularization technique and bring it back to the ideal fit, okay? So that's the general idea. So regularization refers to a set of techniques that are used to prevent overfitting by discouraging complex models, right? So again, in its first place, we want to have a complex model, and then we're going to use regularization to discourage that complexity. Then regularization improves generalization of the model on the unseen data. So we talked about this concept of generalization. So a good model is a model that can overfit first place, and then after that, it can generalize well on the unseen data. So let's say overfit in a train set and generalize well on the unseen data. Okay. So these methods include L1, L2, dropout, early stopping, and data augmentation. So, or at least these are the ones that I cover in this video. Okay. So the first technique is called L1 regularization. So as the name suggests, L1 is going to leverage the idea of using L1 norm. And if you remember from the machine learning concepts course, we know that L1 norm, at least in the two-dimensional space, is nothing but, for example, if I want to go from point A to point B, I can go like this, right? So we also call it Manhattan norm as well. And so basically, if we add a penalty term, which is using L1 norm, to the objective function, we know that this is proportional to the absolute value of the model weights, right? So imagine I have a loss function. It's a function of weights, and it's something I'm going to add, let's actually do it this way. I'm going to add this summation of absolute value of weights, right? Let's say WI. So I call this one L1 norm. If you add this penalty to the loss function like this is called L1 regularization. And this will result in a sparse model in a sense that we have so many weights that the weights are exactly set to be zero. So this property is unique to the L1 regularization when it comes to this kind of family of regularization, right? And if you're curious how this technique is able to set the weights exactly equal to zero, please feel free to review the machine learning part of the course that I talked about how L1 regularization is exactly able to set those weights to zero mathematically. All right, so that was the first one. The second one is L2 regularization. The idea is pretty much the same. You're adding some penalty term to the loss function, but now the penalty term is in the form of L2 norm. And again, if you don't know what is L2 norm, it's simply our Euclidean distance. If I want to go from point A to point B in a two-dimensional, it's like this. And we are adding the weights like squared version of them, right? And so this is L2 norm. So this results in a model with small non-zero weights. And as you can see, this regularization technique is going to force the weights to, the weights that are, well, the idea is that it's going to work on those features that are not necessarily contributing much to the network, or those linear combination of features or engineered features that are not contributing to the network much, and it's going to send the weights towards zero, and it doesn't set them exactly equal to zero. So that's the biggest difference between maybe L1 and L2. The next one is dropout. So this one is maybe one of the most commonly used one, and the technique is pretty simple. It randomly set a fraction of model weights to zero, and it happens only during the training. So this is really important. So it set those weights only in the training part of the process. Okay, this helps to prevent overfitting. I'm going to talk about the dropout in the next slide, so there are more details to talk about. And the next technique is called early stopping. This is probably the one that makes sense. So it's just naturally, you can think of it this way. It's a technique that involves training the model until the performance on the validation set begins to degrade. So we know that, again, there's a slide for this one. Let me not write something here. I'm going to talk about in details later on. So we are going to continue training the model, and as soon as the performance of the model in the validation set is degrading, we're going to stop, right? So this will help to prevent the model to become too complex, right? To fit to the trained data too closely. And the last one that we will cover here is called data augmentation. So this technique is mostly used for unstructured data like images, and it involves generating synthetic data, right? Additional training example, not 100% synthetic. These are slight transformation of the original data, right? So we're going to apply random transformation to the existing data set, and this will help to prevent overfitting by providing the model with more diverse train sets. So if you remember, I think in the machine learning part we also talked about it, that one of the ways to mitigate at least the idea of overfitting is collecting more data. So this is one way to do that, right? All right, now let's start with the details of dropout. All right, so dropout is one of the most popular regularization techniques in deep learning, and it works like this. So imagine this is our network. We have, let's say we have a couple of hidden layers and an input layer and an output layer. And let's say, I don't know, we have 15 neurons here, right? And then at each training iteration, this technique is going to drop out randomly some different nodes to ignore them in the model, right? So for example, if I have 15 nodes here, and there's this concept of dropout ratio, and usually 50% for the networks with large samples and usually deeper network, this ratio 50% works. But if your data set is small, or if you have few number of hidden layers, you have few nodes, 50% is overkilling it. It's too large, right? So you have to see how deep your network is, and then if you have a quite deep network, 50% works. If not, you can try with 5%, 10%, and see what you get, right? But the idea is that here, if I use 50%, I go from 15 nodes to roughly 7 of them, so 7 or 8 of them, right? So randomly at each iteration, so this is important. If you're having 10,000 iteration, this is going to happen 10,000 times, right? So randomly, we are going to shut off 50% of the nodes here because the ratio is 50%, right? So what this does, it's really important. It's going to force the model to identify different types of pathways through the networks. So basically, it helps the model to the different forms of processing the information to be applied, right? And the idea is quite similar to what we covered in random forest machine learning. So remember, in random forest, we said that in order to decorrelate the ensemble of trees, right? In order to decorrelate that forest of trees, let's go ahead and at each split work with a subset of features that are randomly selected. So for example, we said if we have 20 features in random forest, let's go at each split work with 4 of them. So this forced the trees to be more decorrelated. If there is a feature that was dominant in the tree, and in this case in the network, sometimes we want to drop them, because if I drop that dominant feature, I will let the algorithm to learn different, or to try different pathways. So this is very powerful. The idea is really powerful, and that's why it usually works. So as I said, this prevents the network from relying on any single neuron. So this is going to be very important for us, because remember, if you have, let's say, I don't know, if I have 5 features and then one of them is obviously it's really important, so it has 80%, 90% correlation with the target variable, and then you don't want to always try a path like that. Sometimes you want to skip that path, skip that node, right? So this is exactly how the dropout regularization is going to help us to achieve. All right, that was the dropout method. Now let's talk about the details of early stopping. So as I said earlier, this method is going to stop training when the performance on the validation set begins to deteriorate or degrade. So let me actually walk you through to the details. So we're going to start from this graph. We are going to plot a loss function. It's a function of weights and x's versus epoch. Okay. So what is epoch? Epoch is simply the number of complete passes through the entire data set, right? So what does it mean? Imagine you have a network, I don't know, a very simple network with 3 inputs, I don't know, 1 hidden layer with 4, and then 1 output. Let's say this is it, fully connected networks, and we have something like this, right? So we have, and let's say for the sake of argument, the sample size is just 1,000. Okay, so we are gonna train this model. We are gonna do forward propagation, backward propagation, and by passing these observations one by one, right? So observation number 1 is gonna go pass through the entire network. This is forward propagation, generate an output. So let's say this is the output for observation number 1. Then we're going to do observation number 2, and we are going to repeat this process 1,000 times because we have 1,000 observations, right? So we are going to end up with 1,000 predictions. So once we do that one time throughout the entire network, we go forward and backward. This is 1 epoch. So here, if I have, let's say, 2,000 epochs, it means that I have repeated this process 2,000 times, right? I have feed the network of sample 1,000 2,000 times, right? So this is the concept of epoch. And do not confuse this one with the idea of batch. We can do this process of feed forward, actually the back propagation, in different batches, right? And the reason that we want to do it in different batches because we wanted to update, we want to make sure that the training process is not going to take that long. Because, so let me give you an example. If the batch size is also 1,000, so I have 1,000 observations and the batch size is 1,000, I just put all the observations in one batch. If that's the case, then the algorithm is going to update at each epoch. It's going to update the weights. When I'm using the gradient descent, it's going to update the weights only once, right? It's going to use the entire observations, namely 1,000 here, because it's one batch, and then update the weights. Okay. However, I can reduce the size of batch, right? I can say the batch can be 100, the batch can be 1. Usually we do it in the power of 2 because if you want to do parallel processing, take advantage of parallel processing, it's easier to divide it in the power of 2. So for example, we can do batches 128, we can do batch 64, we can do batch 256, right? If we decide to go it this way, and here just for example, I'm going to say batch of 100 because it's easier to use that number. If I use a batch of size 100, the sample is, remember, the sample size was 1000. The batch size, let's say it's 100. So I can have 10 of these batches, right? So it means that in each epoch, the number of times that the weights are going to get updated, it's going to be 10 times. And it's going to be a lot faster because each time the algorithm is using 100 observations instead of 1000 observations, right? So this is, we also talked about this concept when we covered the mini batch gradient descent, right? So let's say the batch size is 100. And then finally, if the batch size is equal to 1, so it means that if I have a sample size 1000, and for each epoch, the weights are going to be updated 1000 times, and each time it's going to use one single observation from the train set. So this is going to be darn fast, right? It's darn fast, but we know that the path to the minimum is going to be unstable. So this has the batch size of 1000 is going to have more stable path toward the minimum. This has less stable, this has least stable, but the point is that this is the fastest, this is second fast, this is the slowest, right? So just keep in mind, what is the concept of batch, what is the concept of epoch. Now we know that, let's go back to this plot, because this is at the core of earliest topic, actually at the core of training your models. You're going to work with this plot a lot because you want to see how the loss is evolving through different epochs, through different number of times that you're going through the entire data set, right? So let's say this is our epoch number 1, and we start from here. Let's focus on the train set performance, right? So the blue dashed line is train set loss, the purple one is validation set loss, right? So hopefully as we increase the number of epochs, the model is going to train, because again, we start from a random weights here, and then as we train the model, the performance is going to get better and better and better, and the loss is going to decrease in the train set. And we know that if I have a deep enough network with reasonable number of neurons at each layer, these models, the deep neural networks, can approximate any function. So there's this theorem of universal approximation theorem, and that's the beauty of deep learning. Actually, it's mathematically we can prove that these neural networks, if they're dense enough, they can approximate any functional form, any pattern out there, right, in the data. So this means that eventually, if you run this for a long time in a train set, you can get lost to a very small number. But we know that this is not the case for the validation set, right? For validation set, we get something like this. If you make the model super complex in the train set, at some point, after some epochs that the model has been trained well in the train set, but after this one, your model is overkilling it. You are making the model unnecessarily complex, and from this point, the model is not generalizable. It's not generalizing well on the validation set, and the performance is going to deteriorate, right? So as soon as you see something like this, it tells you that, okay, the number of right epoch was this. So this is, let's say, epoch star, right? The number of optimal epoch. And then that means that you didn't need to tune the model or to train the model further than this number of epochs, right? Because if you do that, you are making the relationship in the networks unnecessarily complex. So this is a really, really important concept, and I want you to be aware. And so then usually we plot the loss versus epoch. And if you're doing, for example, regression or classification, you can look at different metrics. You can translate it to different metrics. So for example, for classification, you can translate this plot to something like accuracy. The same story, accuracy in the train set is going to increase, and of course you're going to approach accuracy to 1 if the model is super complex, but we don't want to get there. We want to stop here as soon as the model is, we see the sign of overfitting. So this is going to be optimal epoch star. Again, these you can translate from the loss function to the metrics. But usually the loss function is going to do the job. You don't need to visualize the metrics itself. So that was early stopping. One important thing that I wanted to highlight at the very end is that sometimes when you're training your model, you see something like this. So this is, I want you to pay very good attention. It's a little subtle. So this is your loss function, let's say J, or the error, and you have epochs. We know that usually the validation performance should be worse than the train set performance, right? So usually we have something like this. But if you see something like this, let me use the color-coded pen. So let's say this is my performance in the train set. So let me call it train. Or the loss function, not the performance, sorry. This is a loss function performance. And then this one, let me use purple. We start from here, and then somehow we get to a point that your validation loss, so this is val loss, is better than the train set. So this is weird, right? So what's going on here? I want you to pause the video and think about it. And you will see this, you know, when you're working with real world problems, especially if your data set is small, you sometimes will see that, okay, you know, your loss function is getting smaller compared to train set. So what's going on here? So pause the video and think about it. Okay, so hopefully you were able to figure this out. This has something to do with regularizing your train set, right? So because remember, usually we are going to combine these regularization techniques, and most of the time we do early stopping with the dropout. What's going on here in this specific example is that we are applying dropout, and most probably the network was not large enough. So we had a small network, let's say with only one layer or two layers, and let's say 6 neurons, right? So it was a super simple. We have 2 inputs, 6 neurons, and 1 output. Let's say that was the case. So this is 6 neurons, right? And then if you go ahead and drop out 50%, so let's say the ratio of the dropout is 50%, 60%, or something like this in this very small network. So what happens, because the dropout is going to be only applied to the train set, then it means that you are making the model the unnecessarily simple. You're overkilling this regularization, you're overkilling this dropout to already a small network. And that network is not going to learn much even in a train set. Okay, so that's why the train set loss is going to be large compared to the validation set. But why the loss in the validation set is smaller? Because again, dropout is not going to be applied to validation set. You're going to bring back all the 6 neurons instead of 3 neurons. And then that model is more complex, and that small network, because it has 6 neurons now, can learn better in the validation set, regardless of if it has, regardless of the fact that the model has not seen the parameter, the data in the validation set, but it's still able to learn better in the validation set. So that's why you see something like this. So if you're plotting your loss function versus the epoch, and you observe that at some point validation set is doing better than the train set, that's a clear sign that you are overkilling it. You are overkilling the regularization in the train set. And this applies to the regularization techniques that we use and apply them to the train set, namely, for example, the dropout. All right, so the last regularization technique that I cover here is data augmentation. So as we talked about it already, this is nothing but generating some additional data, right? And we're going to do that by applying random transformation to the existing training data. And as I said, we usually apply this data augmentation to the unstructured data like images. And the goal is to improve generalizability and robustness of the machine learning or deep learning model by giving it more information, more data, more diverse version of the train set, right? So here, imagine this is the original data, and I can go ahead and use different random transformation. We can do, for example, crop, we can do symmetry or flipping it, we can do rotation, we can do scale up or down, we can add noise, we can add blur, we can bring some obstruction, and we can finally do some hue, right? It's not limited to these kind of transformation, right? But these are the usually common ones. And as you can see here, we go from a sample of 1 to a sample of 9. Okay, so this is what we call data augmentation. And in general, having more data is going to help the model to train better and avoid overfitting. All right, that was pretty much it for the regularization. So for the rest of this video, I want to cover some random topics like visualization of the neural networks and talk about the tensors. Okay. So here is a very nice visualization that you can find, and actually I highly encourage you to go ahead and try it out on your own. Go to playground.tensorflow.org, and then it helps you to see how neural networks are able to learn nonlinear pattern in the data, right? So it's a very powerful tool that you can play around with, and hopefully you can build a stronger intuition when it comes to neural networks for you. Okay, so let's start. Imagine we are dealing with this data set, which is called donor data set, right? Donut data set, not donor, donut data set, right? So it's like a donut. We have, imagine this is a two-class classification problem, and we have blue observations here, and then the orange ones around it, right? So this is called donut data set. You can play around with different data sets, by the way, if you go to this website. And now imagine we have only two features. Okay, we have x1 and x2. You can go ahead and construct, engineer different features like x1 square, x2 square, or the interaction term x1, x2, but that's not the point, right? The point of doing neural network is, give me the features. I'm going to engineer features automatically, so you don't need to have a domain expert or expert knowledge. You don't need to basically manually feature engineer. So let's say work with those two features. What else do we know? We know that let's work with a very simple networks, only two hidden layers. So hidden layer number 1, hidden layer number 2, and this is going to be your output. We want to visualize the decision boundary. So obviously this is doing a very poor job. Why? Because look at that. What do we have? Our activation function is linear. So basically we are not applying anything to the output layer, right? So if the activation function is linear, we're not doing any regularization. So the regularization is not the point here. And but the point is that it's a very simple network with only two layers, two neurons, and the activation function is linear. The decision boundary is going to be linear, right? So right now, your model is not captured the nonlinearity because of two reasons. Why? Number one is that you are not adding nonlinearity to the network by just using linear activation function. And two, you are having this bottleneck here. So I'm going to talk about this bottleneck in the next one. So what I mean by that, you have two features, and in the next layer, you're using one neuron, right? So this is not a good start for number of neurons in the first layer, because again, let's say you have 20 features or you have 100 features, and in the first layer you only use 50 nodes. So this is going to become a bottleneck because the model is not able to learn enough complex pattern in the data, right? So if anything, the number of nodes in the first layer should be greater or equal to the number of inputs, because we want to avoid this bottleneck, right? And then from there, you can say, okay, did the network learn the low-level features? Let's go to the next layer. Remember, this is hierarchical structure, right? And then now let's learn a higher level features, right? But at the first layer, you have to make sure that the number of nodes is greater or equal to the number of features. So that's one thing. And as you can see, it's not learning much, right? So this is going to your loss is going to be a disaster, right? So you have a very large loss. It's 0.5 here. Okay. Then how can we improve it? We can say, let me go ahead and erase this one. So this is the second one, and in the second one we have enough number of layers. The network is complicated enough, right? We have, let's say, 4 hidden layers. There's no bottleneck here. I have 2 neurons here, 4, and then I can bring it back to 2 and 2, right? So it seems that the network is deep enough. I have enough good number of neurons, but what's going on? Why the model is not still able to generate nonlinear pattern? The reason is that you have to focus on the activation function. So as you can see, and we talked about it in the lecture, if you're using linear activation function, no matter how deep the neural network is, no matter how many neurons you're using, it doesn't work. It doesn't add nonlinearity to the algorithm, right? So that's why, and look at that, in both cases, I let the algorithm run for so long, so 3,000 epoch here, 2,000 epoch here. Regardless of what you do, it's not learning anything, right? And still the decision boundary is linear because you're not adding, you're not incorporating nonlinearity. And as you can see, your test loss is still very bad, right? So this is a bad number. So what can we do? As you can guess, the solution is having a neural network with large enough, let's say, nodes at the first layer, deep enough network, and a nonlinear activation function. So let's consider two more graphs, two more charts here. So this one is the one that activation is okay. We're using nonlinear activation function. But the problem is that, again, I have this bottleneck here. I go from 2 features to 1 neuron, so this is bad. And then I have a very, let's say, a shallow network, only with two layers. Again, if I have even deeper network, but I have a bottleneck here, it's going to hurt the model. Why? Because look at that. I'm using 3,000-ish epoch, still nothing. Still, even though the activation function was nonlinear, I'm not capturing that nonlinearity. And again, my loss function is very bad. Okay, so finally, let's look into the solution. The solution is something like this, right? So if I have a right activation function, let's say ReLU, I don't need regularization. So again, we can play around with those things. I just wanted to show you that the model is capturing nonlinearity. If you have a good activation function, there is no bottleneck here, and the network is not deep. There's only 2 hidden layers, but again, this first layer is not acting as a bottleneck. The number of neurons is greater than the number of features. And then if you do that, look at the loss in the test set, literally 0, and the model learned perfectly, right? So it captures the nonlinearity in the data. So be careful, just adding nonlinear activation function is not enough because you have to make sure that your model is not suffering from that first layer bottleneck. All right, so hopefully this visualization helps you to build more stronger intuition when it comes to deep neural networks, and I highly encourage you to play around with different function, different data sets, different regularization, different activation functions, and see it with your own eyes that how these things, how neural networks work and how it's training the algorithm, the model, based on train set or what is the performance in the test set. All right, so now let's look into the concept of tensors. Okay, so what is a tensor? A tensor is a multidimensional array. You can literally think of it as something kind of NumPy array, right? Why you should know it? Because we're going to work with TensorFlow and in Python, and we need to know how data is stored in a tensor, right? Because again, we're going to work with unstructured data, and it's not as simple as a structured data that you have rows and columns. So you have multi-dimensions. So let's say how we can figure out what are those dimensions, right? So in order to make sure that we are on the same page when it comes to terminology, let's do a quick review of different rank tensor, right? So what do I mean by rank? So a rank of a tensor is a number of tensor axes, right? So we can have rank 0, rank 1, rank 2, rank 3, rank 4, and sometimes rank 5. So let's look into them. And when I talk about size of a tensor is a total number of items in a tensor. So I'm going to walk you through multiple examples, and hopefully it makes a lot more sense. So we have a table here. The first one, we say, okay, different ranks. Then the second column is the code in TensorFlow. The third one, I'm going to show you the shape and some examples. So starting with the first one, this is our scalar, right? So rank 0 tensor, or we call it scalar. In TensorFlow, we can do tf.constant, and for example, number 4, right? It's the shape of this tensor because again, it's empty shape, because it's rank 0. So if you assign something like this, or you see something like this, it means that it's a scalar, it's a number. What is example? One number, number 4, number 1, right? The second one is a vector, right? So vector is rank 1 tensor. And so for example, we have a tensor vector with numbers 2, 3, 4. The shape, this is important, right? The shape of the vector, you have to show it with with 2 arguments. The first one is literally Here we have, for example, how many numbers we have, 2, 3, 4. And then the second one, you have to leave it empty. Okay, so this is the way we're going to save a vector in a tensor. So the shape is going to be 3 and empty, 4 and empty, and things like that. So what is the example? Here's the example. Again, this is a vector. The third one, matrix. So matrix is rank 2 tensor. So we can define it in a TensorFlow like this. And just pay attention to the number of brackets and colors that I'm using. So here I'm using red, for example. So there's an outer bracket and inner bracket. So I'm going to put together 3 of these vectors, and I'm going to stack them and then using an outer bracket. And then what is the shape of this? It's a matrix, right? I don't want to overcomplicate this. It's a matrix of 3 rows and 2 columns, right? So 3 rows, 2 columns. So this is, by the way, that the way that we're going to save grayscale images, because in grayscale images there's no channel, there's no RGB channel, there's no third dimension. We can have only, so for example, I can say this is a 256 by 256 pixel image, grayscale image, right? I can save it as a matrix. And then the next one is rank 3 tensor. So for a rank 3 tensor, again, just look at the colors that I'm using here, outer bracket, inner bracket. It's not that difficult to follow, but the idea is that I think if you see this one, it's the shape, it's going to be a lot easier. So we have 3 by 2 by 5, rank 3 tensor, right? And we can visualize it differently. So we can say, this is 3 batches of data, right? 3. And then at each batch, we have, 2 rows, 5 columns. So this is one way to show it. You can show it like this, 2 rows, 5 columns, 3 batches of data, or 2 rows, the 3 batches of data, and then 5, let's say, features, right? And so this is probably one of the most commonly used one when it comes to visualizing these tensors, rank 3. But again, it really doesn't make a big difference. As long as you understand what we're talking about, you're in good shape. So the next one is rank 4. Let's look into that one with a more complete example. Okay, so now let's talk about rank 4 and rank 5. These are higher dimension tensors, and these are the tensors that we usually save our unstructured data in, right? Usually it's 4 dimension. We rarely go to 5 dimension, right? So let's say we have a rank 4 tensor. How can we do it in TensorFlow? To make it easy, I just used zeros. It's going to generate much of zeros, right? And now I have 4 numbers, 3, 2, 4, 5. So what does it mean? Usually the first number, we call this batch index. Okay, so this is our batch index. So for example, I have 100 batches of data. This is literally your sample, right? That comes in batches, right? So this is the batch index. Then the second one, number 2, 4, 5, it's basically our rank 3 tensor, right? So we can think of it as, look at that, I have 3 batches of data. And then for each of them, we have, let's say, 2 is height, and then 4 is our width, and then 5 is, let's say, the number of features we have, right? So this is rank 4. And we have, for example, this is axis number 1, this is the last axis, or axis number 3, so 0, 1, 2, 3. So what information we can extract in Python? So here's a sample code for you. You can give it a try. So for example, I created this rank 4 tensor. So let's see what can I extract. So let me use the right tool. I can say, what is the type, right? If I do .dtype, it's going to give me the type. The type is going to be float 32. I can look at the number of axes. So this is literally the dimension, number of dimensions. So the number of axes is the same as number of dimensions in TensorFlow. Don't confuse it with because sometimes we have, we say structured data is multidimensional, feature space has 100 dimensions. Don't confuse these two concepts, right? So here we're talking about axes, number of axes as dimension. So here I have 4 axes, it's 4 dimension. I can look at the shape of a tensor. So the shape is, again, 3, 2, 4, 5. This is the one that you should know, right? So when it comes to writing codes, so this is really important. You should get a good grasp of what is the shape of a tensor. Because When it comes to applying deep learning in Python, a good chunk of it is preparing the data, right? To come up with right tensors, to save the data, pre-process the data, because the rest of it is super simple. And you're going to see the next part that I go over deep neural networks in Python. It's not that complicated to apply it in Python, so maybe more, at least for beginners, right? When we're using the sequential approach when it comes to TensorFlow. Then the next thing you can extract, off of this shape, you can say, give me the first axis, give me the last axis. Again, here the first axis was 3, the last axis was, so here's the first, the last one was 5. And then finally, what is the size of your tensor? So the size is a multiplication of all these numbers, right? 3 by 2 by 4 by 5. So it's going to be 120 in this example. Okay, so I think we talked about it. The axes are, let me use the right pen, are ordered from, usually that's the case, from global to local, right? So you start from how many batches you have, and then you go down. And then the first axis is usually our batch axis, okay, or batch dimension. All right, so that was the rank 4, and now let's look into the next one, which is the real-world examples of data tensors, right? So the data that we're going to work with is either a structured data that it's going to come as a vector data, right? We call it rank 2 tensor, or it's an unstructured data, and we usually require rank 4 tensor. We don't need to go beyond that, right? But let's look at some examples in more detail. So again, vector data, we said that it's a rank 2 tensor, and it's like this: samples, features. Remember, we go from global to local, right? So we start from how many samples you have and how many features. So each sample is a vector of numerical attributes, right? So I don't know, you're quite familiar with this. If I have a data set like this, x1, x2, let's say x50, and if I have observations from 1 to 1000, so what is the shape? The shape is going to be 1050. Okay, samples and features. And of course, if you have, well, this is my x variable, right? Then the next one is, so for example, time series data or sequence. So we're going to look at some examples on this slide and the next one. So let's look at the time series structured data. So time series data or sequence data, it's a rank 3 tensor, and it's a rank 3 tensor. The batch is going to be samples. Then the next one is going to be time step. The next one is going to be features, right? So each sample is a sequence of feature vector. So again, if I have, let's say, 100 observations, this is number of samples, and then I have features, and it's going to span through a time step. Okay, let me give you an example for time series. It makes sense. So imagine we have 250 days. This is a stock market, right? And we are collecting information based on hourly price. So in each day, how many time steps we have? So each trading day is 8 hours. Let's say this is a stocks and it's only open for 8 hours. And then I'm collecting two information. So what are the features? The features that I'm collecting on a stock is it can be price and its volume. So how do I write it as a tensor? So maybe pause the video and think about it. Okay, so I'm going to have, we start from the samples, 250, and then what is the time step? For each day, it's going to be 8 hours, and how many features we have? 2. So this is our tensor for structured data, for example, here, time series. Okay, then for unstructured data, for example, images, we usually do rank 4, even if the image is grayscale, right? So let me walk you through that. What do I mean with that? So it's a rank 4 tensor. The shape is, we start with samples. So for example, here I have 2 images, so the sample is going to be 2. Height, width, so this is a dimension of the pixels, right? So for example, this is my height versus width. And then channels. So and a colorful picture has 3 channels, RGB, and a grayscale has 1 channel. So if your image is colorful, this channel is going to be 3. If it is grayscale, it's going to be 1. Okay. Now, so for example, let me actually say this is 1024 by 1024 image, right? So pause the video and think about how you are going to write the rank 4 tensor. What is the shape of it? So what is the shape of this example that you're seeing here? Okay, so you have two samples, two images, height width 1044, 1024, 1024, and the channel. How many channels do we have? 3. Again, this is a RGB. So here, number of channels, we call it color channels. So this is a shape. And now imagine you have, let me give you another exercise to solve. So imagine you have 128 grayscale, let's say grayscale images of size 200 by 200. Okay, so how do you write the shape? So what is the shape? Well, let me actually make sure that if you're reviewing these things later on, you don't get lost. So what is the shape of this example? Again, maybe you want to pause the video and think about it. Okay, so we have 128 samples. This is a batch index. Then the size is going to be 200 by 200. So I have 200, 200. How many channels we have? 1. Again, usually we save the grayscales like this. So we are going to define it as a rank 4 tensor. Okay, so the last one that we can talk about is rank 5 tensors. And example is video, right? So let me walk you through this example. Again, rank 5, we are going to start from global samples. Now we're going to add frames, height, width, channel. So the only new thing is frame here. As I said again, we go from global to local. So start from samples and then frames and then height, width, channel. So what is a video? After all, a video is a sequence of, let's say, images, and we're adding that sequence here in the frames. That's simple, okay? Each sample is a sequence of length frame we talked about in image. So for example, let's think about, I want you to think about shape of this example. What is the tensor shape for a 60-second 144 by 256 video clip sampled at 4 frames per second? So I want you to pause the video and think about it. Okay, so hopefully you got the answer. Let's start by samples. How many samples, how many videos you have? In this example, 1. How many frames you got? We got 4 frames, and each frame has 60 seconds, right? So it's going to be 4 by 60, 240. And then height, so this is the easy part, 144, 256, and what is the number of channels? 3. So this was one video, right? If I stack multiple of these videos, let's say if I stack 5 of them, then this is going to change to 5. If I stack 10 videos, it's going to change to 10. Okay, so that was pretty much it. So this last 2 slides, I just want you to review them a couple of times, because when it comes to the coding part, sometimes students usually have hard time to figuring out what is the right shape, how they can transform the data, how they can prepare the data. So this is a part that I want you to pause for a second and make sure that you get a good grasp of the concept of shape of a tensor. So we already covered everything we need to know for the course. Okay, so the last thing I want to cover in this video is different type of neural networks. So we already covered this in the first part of the module when we talked about introduction to deep learning. And basically, this is going to give us an idea of how the rest of the course is going to look like, right? So we are going to start applying whatever we learned today. This is our standard neural network in Python and TensorFlow. So it's going to be a lengthy video, plus 1 hour. So I encourage you to do it in one sitting. Just make sure that we're going to cover different ways that we can use TensorFlow. We can use it as a beginner, just using sequential class. We can use it as a more intermediate user by using functional API, or we can use it as an expert by doing subclassing model, right? For this course, I'm going to stick to the intermediate level because that's what most people do in industry. As long as you're a PhD researcher, you're working on a unique question, you don't need to do the subclassing models, okay? So I'm going to do the functional API when it comes to applying all these things in Python. This is our standard network, and in the next module, we are going to do some image processing, deep computer vision. So that's why we have to work with different structure, different network. We call them convolutional neural networks. So that's our module number 5. And then we talked about time series, recurrent neural network. This is our module number 6, deep sequence modeling. And then finally, we're going to talk about transformers. So this is another state-of-the-art architecture, which is basically based on the concept of attention layers. So this is our module number 7. All right, so that's pretty much it. Until the next one, take care.